Okay, in our last topic, topic 12, we talked a bit about magnetism, and we talked about really permanent magnetic fields. Okay, magnetic fields from magnets. What we're going to look at in this topic, in this lesson, topic 13, we're going to talk about electromagnetism. In other words, a link between magnetism and electricity, or electric fields and magnetic fields. So, the first thing we'll look at is something that's known as Oersted's discovery. And a guy by the name of Christian Oersted discovered, and legend has it that it was kind of discovered by accident, but that's irrelevant right now. But basically what happened was he set up a little experiment after he noticed something happened. But this is the experiment he used. He basically took a conductor, a current-carrying conductor that you can see here. Here's the wire, straight up and down, vertical. And he put a number of compasses around it. And what he found was that as soon as he turned on the power source, as soon as he connected the battery, and electrons would go from one side to the other, in other words, electrons would do this. They would leave the battery, come up this way, leave the negative, right? Come here. Then the current would flow up through here, and then back here, down this way, back into the battery. So the current would start to flow. But what he noticed was, as soon as he turned the current on, the needles on the compasses would all move. In other words, it seemed like there was a magnetic field that depended on the current. Because as soon as you turned the current off, the needles would all go back to pointing north again. But while it was on, here's what would happen. This needle would point that way. This needle would point that way. This needle pointed that way. And this needle pointed that way. Okay, so in other words, they kind of seemed to point around in a circle. And that led Oersted to believe that around that current-carrying wire there was a circular magnetic field, because that's what the compasses showed. In fact, if you took a compass and actually moved it all the way around, you'd actually see that compass needle would actually trace out a full circle. A full circle. So there's a circular magnetic field around a straight conductor. Now, there's an easy way, it turns out, to figure out the direction of that magnetic field. And it's called the left-hand rule. And there are actually three left-hand rules, as you probably remember. The first one is the one for a straight conductor. Okay, so left-hand rule for a straight conductor, and I always tell my students to use their pencil. Pencil represents the wire. The tip of the pencil is the direction that the current points. So you hold it with your left hand, with your thumb pointing in that direction, and your fingers will wrap around your pencil in a circular direction. And the direction that your fingertips point is the direction of the magnetic field. So in the one you see here on your screen, in the example you see here, your thumb is pointing this way because that's the direction of the magnetic field. And you'll notice that your fingers on the bottom of it are pointing out of the page, out of the screen, and then they're pointing up on the front of the wire, they're pointing in on top of the wire, and they're pointing down on back of the wire, which is what's giving you this circular pattern right here. See, up on the front, down on the back, out of the screen on the bottom, into the screen on the top. Those are the directions. Those are the directions. We call that left-hand rule number one. You need to know your left-hand rules, because I can guarantee you you're going to need to use them on your public exam. So be familiar with them. And we're going to do some practice in those now in just a minute. Okay, but that's only for a straight conductor, a straight piece of wire. That's what left-hand rule number one applies to. But wires are not always straight. Often they're bent into a loop or a coil. So if we take this straight conductor and we bend it into a loop, okay, just look. This X right here means that it's going into the page. That's a convention that we use. So the current's flowing into the page or into the screen. It's going in, it's going up around, it's coming back this way, and we put a dot there to show that it's coming back out of the page right there. So if we use our left hand, first of all, pointing your thumb into the screen, you'll see a circular field going counterclockwise like this. And if you do it at the top where the current is coming back out, your fingers are pointing in a clockwise direction. But the important thing is here in the middle, you'll notice that both magnetic fields are pointing to the left. They're both pointing in the same direction. Okay, when that happens, the field actually gets stronger. So by taking this piece of wire and bending it into a loop, inside that loop we get a stronger magnetic field. The field is actually stronger inside. So we can strengthen our magnetic field by doing that. In fact, we could also add more loops with the same piece of wire, and we could make what's called a coil. And all the fields then on the inside of the coil would point in the same direction. That would make it even stronger again. And there's a left-hand rule for that too. We call it left-hand rule number 2. But first, here's what it would look like. You took a single loop of wire and passed current through it, and you sprinkled some iron filings down there. This is what the field would look like. Okay, you can see the circular magnetic field around the sides, top and bottom. But you can see in the middle these really dark areas. That's showing where the fields are really starting to add to each other. And you're getting very strong fields. When you put more than one loop together, make a coil, which is often called a solenoid, by the way, and you see this. And then you see, look, on the top, right? Look how it curls around like that. And that should remind you of a bar magnet, because that's what the magnetic field around a bar magnet looks like as well. Very much like that. Okay, up around here, down around and in. Same thing on the bottom. Look, out here, kind of comes all the way up around and goes back in again. Exactly like the field around the bar magnet. Identical. Only this is with a coil. A coil of wire that's not a magnet, not really, but it has magnetic properties as long as there's current flowing through it. As long as there's current, it has magnetic properties. So that's a solenoid. Now there's a left-hand rule that can tell us which direction that magnetic field is in. And it's kind of the opposite of left-hand left-hand rule number 1. Remember, in left-hand rule number 1, your thumb pointed in the direction of the current, and your fingertips pointed in the direction of the magnetic field. Well, left-hand rule number 2 is the exact opposite of that. Your fingertips point in the direction of the current, so you grab the coil, and think of the coil like a paper towel roll. You grab your hand around a paper towel roll so that your fingers are pointing in the direction that the current is flowing through those loops. Your fingers follow the current. When you do that, your thumb indicates the direction of the magnetic field inside the coil. So, because in this example your thumb is pointing to the right, that means the magnetic field lines inside the coil are pointing to the right. And they're coming out of this end of the coil. Now, if they're coming out of this end of the coil, that means this must be like a north pole. That's like the north pole of a bar magnet. Same thing. Because field lines always point away from the north. So, in essence, what we usually say is that your thumb points north. Whatever end your thumb points to, that's the north end of the coil. That's the north pole of your electromagnet. Because essentially that's what this is, an electromagnet. Okay, and we can vary the strength of this magnetic field by changing some things. There's different variables we can change here. Okay, for example, we can increase the current in the coil. More current, stronger field. In fact, it's a direct relationship. The strength of the field varies directly. It's directly proportional to the current that flows through the coil. In other words, if we double the current, we double the field, the strength of the magnetic field. The number of coils, number of loops or turns in the coil, the number of times it's wrapped, that's also a direct proportion to the strength. In other words, if we had two coils, one had twice as many loops as the other, and they were the same size loops, same distance apart, all that stuff, and the same amount of current, everything else being equal, then you'd have twice as much in the one with twice as many coils, twice as much magnetic field strength. There's a direct relationship again. The size of the coil is important. The smaller the coil, the smaller the diameter, the smaller the size of the loop, the stronger the field. Okay, the tighter you can wind your coil, the stronger the field is going to be. And the one that affects it the most, the biggest impact of all, is the last one here. The type of material that we put in the center. That has the largest impact. For example, by taking a coil of wire and putting an iron core in the center, we can magnify the strength of that magnetic field by over 1,000 times just by simply putting a piece of iron in the center. Because ferromagnetic materials can really increase the strength of an electromagnet. Okay, the strength varies directly as the measure of ferromagnetic properties. And we call that the magnetic permeability. And we're going to look at that a little more in another topic. But magnetic permeability tells you how easily the domains line up. Is really what that's a measure of. The higher the number, the more easily they line up. And the better a material it would be for increasing the strength of our electromagnet. So there are the four things. You should know those because they could show up, particularly in a multiple choice question. Quite possible. So so far we've done 2 left-hand rules, one for straight wires, left-hand rule number 1, thumb in the direction of the current, fingers in the direction of the magnetic field. Then we talked about left-hand rule number 2 for coils, which was fingers wrapping around the coil in the direction of current, and your thumb pointing in the direction of the magnetic field, or to the North Pole. Okay, and there is one more, but the third one deals with the direction of force. So we're going to leave that one for now. Then there's adding a core. We just talked about that. Different substances, depending on how much they have in the line of magnetic properties. In other words, how ferromagnetic they are. Different ones can affect the strength of the electromagnet. But like I said, this is the one that has the largest impact by far. In order to have the same impact as adding a metal core to your electromagnet, like you'd have to increase the current by like 1,000 times bigger. The wire probably wouldn't even be able to handle it, for example. Okay, so those are the things that affect the strength. So that magnetic permeability is a really important thing. Okay, so let's take a look at some of those things now and how they show up as questions on public exams. And like I said, the third left-hand rule, we're going to talk about that one in our next topic, topic 14. Anyway, which one best describes the magnetic field lines around the current-carrying conductor shown? So look at this guy. That dot tells us that the current is flowing towards you. And the way I tell my students to remember it is an easy way to remember it. Think about an arrow. Okay, if you're doing archery in phys ed class. If the arrow was coming towards you, you see a point. Right? Coming towards you, you see the point. If the arrow was pointing away from you, you probably see the tail feathers, which would make an X. Okay, that's an easy way to remember it. So this one, the dot means coming towards you. So you hold your left hand up with your thumb pointing towards you, and if you do that, your fingers point in a circle like this. Okay, your fingers point in a circle like that. Okay, and the direction that your fingers would be pointing would be clockwise. Like this. That's the direction your fingers would point. So, in other words, we got clockwise, concentric circles. Now, concentric, if you haven't seen that word before, all that means is that circles that share the same center. Okay, so really there's more than one circle. There's bigger ones and bigger ones and bigger ones as you go further out from the object. The second question there on the page gives you a solenoid. There's a coil there, and it's surrounded by 4 compasses. Which compass reading is correct? Well, the first thing we're going to do is we're going to use left-hand rule number 2 to see what the polarity of that solenoid is. So you take your left hand, you hold it out so that your fingers curl around and point down in the front. They point down the front because that's the direction the current is flowing here. You can see it in the diagram. Look, current flowing down. So your fingers point down, and when you do that, your thumb actually points to the left. So what that tells you is that that's a north pole right there, that's a south pole right there. And now what you got to remember is that your field lines do this. Okay, I'm going to draw the field lines in red. Your field lines come out of the north pole like this, go around the coil, and then come back in down here like this. So out this way, back around this way, and in there. Now remember, the compass needle is going to line up with that field. So the only one that's doing that is A, isn't it? A is the only one that's actually lining up with the magnetic field. So that's the right answer. B and C, in order for B to be pointing in the right direction, it would have to be pointing this way. But it's not. D would have to be doing the same thing. C would have to be pointing this way to be correct. Okay? There's the directions all those compass needles would point. So the only one that's actually shown in the right direction is A. All the others are pointing in the wrong direction. So that's how you do that. But you got to remember what the shape is. Now this one here, very similar to the first question we just did, except this time there's an X. And remember, X means the current is going away from you or into the screen. So you hold your finger out, your thumb pointing in, your left hand, your thumb pointing in away from you into the screen. Your fingers then would point in a counterclockwise direction, which means that the correct answer is B. That's all you got to do. That's all you got to do. So you got to be careful with these. You got to be careful with these. But if you know your left-hand rules, this stuff is pretty straightforward. Let's try another one. Who was it that discovered a magnetic field is created around the current carrying wire? Well, that was a guy by the name of Oersted. Christian Oersted. Okay, and every now and then they throw one of these on. This is actually what we call a level 1 question. Basically, you know it or you don't. Okay, and it's usually just either a very simple calculation or some fact like this that you should remember. But that's what we call Oersted's discovery, right? A magnetic field around a current carrying wire. All right. The next question, the directions are a little hard to pick out, so I'm going to fill them in here. North, south, east, and west. And we want to know, right now the compass needle is pointing that way, but as soon as we close the switch, that compass needle is going to move. That compass needle is going to move. It's going to align itself with the magnetic field around that coil. As soon as we close the switch, current will start to flow this way. That means up the back and then down the front like this. Like that. That's what's going to happen with the current. So when we do that, now I can use my left-hand rule number 2, wrap it around the coil so that my fingers point down the front, and if I do that, my thumb points this way, telling me that's a north pole and this is a south pole. Now if that's a north pole, remember, the magnetic field lines are going to point out like that. So which way is my compass needle going to point? Now don't say north. North is actually straight up, right? My compass needle is going to point this way. Straight over, pointing at the west, isn't it? So the answer is actually west. You got to be careful, because some people will say, oh, north or south, but it's not. Because of the way the compass is aligned there, the compass needle is actually going to point directly away from that north pole, which means it's going to point at the west of the compass. Okay, so you got to be careful. You got to watch what you're doing. Next question. Which one of these shows the magnetic field on both sides of a current carrying wire? Now, remember your left-hand rule number 1. This time it's a 3-dimensional type drawing. So your current in every one of these is flowing up, straight up. So you hold up your left hand with your thumb pointing straight up to the ceiling. And if you look at your fingers, to the right of your thumb, they would be pointing towards you. But if you rotate your hand the other way, to the left of your hand, your fingers will be pointing into the screen. Okay, so that, right, these here, this means into, this means into, this means out, this means out, this means in, this means out. Remember, right? The dots and the X's mean towards you or away from you. The dot is out towards you, and the X means into the screen or away. So there's what we got. Now, which one is right? Well, when you hold up your left hand, you'll see that on the right hand of the wire, your fingers are pointing out towards you, which means dots. On the left hand of the wire, your fingers will be pointing into the page, which would be X's. So the correct answer would actually be this one. Okay, you got to be careful. Again, right? See, this is actually a circular field. If I actually drew it, I'm going to draw it in red. If I actually drew that field, here's what I'd actually end up with as a three-dimensional view. Okay, out this way, in this way. Okay, think of it in 3 dimensions. Hold your pencil straight up in front of you and grab it with your hand. That's what it would look like. Your fingers will be pointing towards you on the right side of your pencil, but away from you on the left side of your pencil, which is what B is showing. So that's the right answer. Next question. This is a long answer question. Okay, this was on the exam, the public exam, not that long ago. You got 2 diagrams they're showing, and we've got a metal rod with a mass M. Doesn't tell us what the mass is, but it doesn't matter because we're not asked to do any calculations here. And it's suspended in a magnetic field using 2 wires. Now in diagram 1, there's no current. So there's really only, let me draw the forces. There's a tension right here, there's a tension right here, and there's a force of gravity right here. Those are the only forces acting on that wire in diagram 1. The only forces. Now it says in number 2, there is a current flowing through the wires. So the current's coming down the first wire, up the one on the right, which means it's flowing to the right in the middle of the wire here, right here, flowing to the right. So we're going to use our left-hand rule to see which direction the magnetic field is for the wire itself. And let's see what happens. So if I drew the magnetic field for the wire itself, okay, let's draw it in 3 dimensions. So it comes up around like that, down around, and then back like that. Okay, and what you see is the current is flowing into the screen at the top there and out of the screen at the bottom. So if it's flowing into the screen on the top, okay, up here, it's flowing into the screen. So if it's flowing into the screen right here, what does that do? Well, we've got a magnetic field, the permanent magnetic field right here, a constant magnetic field, all these dots represent that, that's pointing out. And the other field, the one caused by the current, is pointing in. So what happens there is those 2 fields get weaker. Weaker field on top because the 2 fields are opposing each other. That makes them weaker. But on the bottom, we get a stronger field. On the bottom, we get a stronger field. So because we get a stronger field on the bottom, that has a tendency to push those wires up. So what we've actually got here is, on this diagram, we still got 2 tensions right here. We still got a force of gravity pulling down right here. But we've also got a magnetic force pointing up right there. So because that magnetic force is pointing up, that would actually reduce the tension in the wires. In fact, if the current was strong enough, it could actually reduce the current to 0. You could actually eliminate the current completely if the current was strong enough. You could actually eliminate the tension in those wires completely. In other words, the wire would just be suspended. If you put enough current through, you could actually make it start to move upwards. Okay? So, this one has less tension because we got that extra force. Now, if we had moved the current in the opposite direction, it would have been opposite. Right? If the current had been flowing to the left instead of to the right, that would have made the field stronger on the top and weaker on the bottom, which would have meant the wire was being pushed downwards by the magnetic field, and that would have increased the tension in the wires. Okay, so it really is dependent on the direction of that current. So you really got to watch that. All right, one last question. This one is very similar. We got two metal rods, A and B, supported in a vertical wooden rack. Okay, so they're just laid here. Now, as soon as we connect that battery, one of the rods moves, one of the rods jumps. So let's look at what happens. The negative terminal of the battery is this one right here. So that means that as soon as the battery is connected, current starts to flow this way. There, through this wire like that, and then up through here, through wire A in the opposite direction, and then back to the battery. Now what that does is this. Let's draw the two magnetic fields. Okay, I'm going to draw them in two different colors. So I'm going to say magnetic field B. If I just draw it as dots and X's, just watch. Your thumb points left. So that means your fingers are pointing out of the page at the top. So like this. And they're pointing into the page at the bottom. So like that. There's your magnetic field for wire B. Then you've got another magnetic field for wire A, and what happens is, since it's pointing in the opposite direction, that means your fingers are pointing in on the top. And actually, I intended to do that in a different color, so let's do that. Let's do that one in green, so that they are separate. So here's the green one for A, and out of the page on the bottom. Out, out, out. Now, what's happening is in the center, where A and B are closest, in the center, the two fields point in the same direction. When that happens, when two fields are pointing in the same direction, the field gets stronger. So it's getting stronger here in the middle. So what that means is A and B are actually going to repel each other. It's just like bringing two north poles of magnets together. The field gets stronger and they repel each other. All right, so because the field gets stronger like that, wire A will actually jump upwards. A jumps up. Okay, B can't jump down because there's supports there that are preventing that from happening. Right? It was on the rack. And because it's on the rack, it can't go down, it can only go up. And it's not going to go up because it's not attracted to the other wire. It's repelled. So because of the repulsion, A jumps up. Because B can't go down. That's why. All right, and that's it. Those are the types of things you can expect to see. And always remember your left-hand rules. Your left-hand rules are the key to these magnetism questions. They are the key. Okay, so we're going to stop right there. That is electromagnetism. What we're going to look at in our next topic, topic 14, is we're going to take a look at the motor principle. And there's another left-hand rule then, left-hand rule number 3. But we'll deal with that in topic number 14. So as I usually say, good luck with your studies. Work hard, and please do come back and watch some more of these recordings because they can only help